Good morning, children. I hope you understood these numericals well. Most of you had done the homework and it was correct. So we have done till 27. Okay, we are left with 28, 29, 30 and 31. And 30th is not in the syllabus because they've said only 3 resistors has to be. You'll be given a circuit which has maximum 3 resistors. Okay, so this will not be there. So you can strike it off. So we are left with 28, 29 and 30. So the 28 I'll be doing now, and these two are homework. 29 and 31 are homework. Okay, so we'll do 28th now. The circuit diagram in figure 8.53 shows 3 resistors 2 ohm, 4 ohm and R ohm connected to a battery of EMF 2 volt and internal resistance 3. Okay, here there are 3 resistors connected to a. So far we saw there were either 2 parallel resistors or 2 series resistors connected to an EMF and internal resistance. Now we have 3 resistors, 2 parallel and 1 in series, and the entire thing is connected to a battery which has a EMF and terminal voltage also. So we have to calculate few things. So I'll quickly draw the circuit. 2 ohm, R ohm, 4 ohm and 3 ohm, and you can put a small battery here, resistor here, internal resistance, that is 2 volt and 3 ohm, and current is given as 0.25 ampere. Okay, so first one we have to find. So in this, one resistor is unknown but current is given. Okay, one resistor value is unknown but current is given. So with that we can manage to find. First is PD across 4 ohm resistor, potential difference across 4 ohm resistor. So I into R. Okay, current is 0.25, and because they have asked across 4 ohm into 4, that is 1 volt. Second one, PD across internal resistance. So PD across small r, that is potential drop basically. I into small r, 0.25 into small r is 3, that is 0.75 volts. Third one, PD across R ohm or 2 ohm resistor. Why they have given R? Because they are parallel. PD across these two will be same. Either you can say PD across R ohm, PD across 2 ohm, both will be the same. So PD across R ohm or 2 ohm resistor. Now in this, we can't find the total resistance because one resistance is unknown. R value is not known. So you can't find the equivalent resistance of this parallel combination. So we cannot use this formula which we are usually using, I into R. Okay. So we have to think of some other way of using it, some other way of finding it. Okay. So we saw that this potential drop is 0.75 volt. This potential drop is 1 volt. So this potential drop will be across this parallel thing. Okay, if I take it as X. So you remember in series combination, when 3 resistors are in series, we can say that V is equal to V1 plus V2 plus V3. Supply voltage is equal to the potential drops in each resistor. See, this is the thing I'm talking about. So 3 resistors, and then there is a potential drop. There is a supply voltage. V is equal to V1 plus V2 plus V3. V is the supply voltage is equal to potential drop across, potential difference across each resistor. So same principle I'm going to use. 2 volt is the supply is equal to the potential difference here 0.75 plus the potential difference here plus X. Okay, so 2 is equal to 1.75 plus x, or x is equal to 2 minus 1.75, that is 0.25 volts. So potential difference across this parallel combination is 0.25 volt. Now D part, they're asking you to find the value of R. Now that you know the potential difference, we can use the other formula. V parallel is equal to I into R parallel. Okay, V across this parallel combination will be I into R parallel. Now what is our R parallel? 1 by Rp is equal to 1 by 2 plus 1 by R. So from this, R parallel will be V by I, V parallel by I, that is V parallel across parallel is 0.25 upon current is also 0.25. So it will be 1 ampere. It will be 1 ampere. So, sorry, 1 ohm. So 1 ohm is equal to 1 by 2 plus 1 by R. We have to find 1 by R, keep that this side. So 1 by 1 minus 1 by 2. So 1 minus half will be half, or R is equal to 2 ohm. So the unknown, this resistance R's value is 2 ohm. Have you understood, children? So this is how, if you are given a circuit with 2 parallel and 1 series, you have to do. This is also the same type. Here they have given an ammeter and they have given a resistor. You can just take this as a resistor of 0.8 ohm, and this will be the same as this. Hope you got it. Now because here one resistance value, unknown value, here it was unknown, here it is known. So you don't know the current here. So you will find the current using formula E upon capital R plus small r. Small r is this, capital R is the equivalent resistance of this part. Then rest all you have to do the same way. Okay, children. So with this, we are coming to the end of B part. Now, there is a small correction here. It's given C part, but this is to be considered as Chapter 9 Part A. Chapter 9 Part A. Why? Because in Chapter 9, A part is fully cut. Okay, there is one small portion. Otherwise, A part is fully cut, and you have already this chapter has two parts only. So, one part was fully cut. This chapter has 3 parts. So, to equalize it, okay, you can consider this as Chapter 9 Part A. Chapter 9 Part A. Okay, and Chapter 9 Part B, I'll tell you later. So, we are starting a new chapter now. Okay, so this is also related to, so these 3 chapters okay, 8, 9 and 10 are related to electricity, electromagnetism and all that. Now this chapter, the heading goes like this: electrical energy and power. Electrical energy and power. Now we are coming to the practical aspect of it. So far we saw current, voltage, potential difference, all that related to electricity. Okay. Now at home we use electricity, but not directly. In the sense, you don't use current directly to pass through something. It is always converted from one form to another. So the various applications, various things. If it is a bulb, electrical energy is converted to light. Okay, if it is geyser, electrical energy is converted to heat energy. So in all the practical applications, we won't be using electrical energy directly. It is always converted into some other form, and this is the practical application thing. Now, how to measure the electrical energy consumed? Okay. Now, basically, you all have heard about electricity bill. Your parents might be paying electricity bill every month, and so how do they calculate it, and how can it be calculated and all that? So we are basically we are consuming electrical energy. So how to calculate it so that we can pay the electricity bill? Before going into that part, we should study the formula for electrical energy. Electrical energy. Now, um, the formula for the other name for energy is basically work done. Remember, work done is also basically energy. Now, if you remember this formula for potential difference, V is equal to work done to carry a unit positive charge from one place to another. This is the formula for work done. So work done, let's not take WD, we'll take W, is equal to V into Q. So when I consider electrical energy for work done, I use this formula, W is equal to V into Q. If it was a displacement, okay, in chapter 2 we did that, you took force into displacement. Here, by applying force, there was some displacement. In that case, to calculate work, I use this formula. In this case, electrical energy, there is some potential difference, and because of it, some charges flowing. So to measure electrical energy, okay, or work done, electrical energy, basically it is electrical energy only, okay, is equal to V into Q. Now, Q is not a very, we don't calculate Q practically, but so you know the formula for I is equal to Q by T. From this, I get Q is equal to I into T. So instead of Q, okay, Q is not generally a measurable one. I into T is measurable one. Current we know, time we know. So I'm just replacing Q by I into T. So this helps me to get this first formula for electrical energy, V into I into T. Voltage into current into time for which the current flows. That will give me the electrical energy consumed by a particular appliance. Okay, I can have two more formulas. Okay, now instead of V, if I want the formula, so you know that V is equal to, according to Ohm's law, V is equal to IR. So instead of V, if I write IR into IT, so this will give me another formula, I squared RT. Another way of writing is, instead of I can write V by R. So V into V by R into T, that is equal to V squared by R into T. So I have three formulas for electrical energy, V into I into T, or I squared into R into T, or V squared upon R into T. Now, in the numerical, depending upon what is given, if they give you V, I and T, use this formula. If you know I, R and T, use this. If you know V, R and T, use this. So, depending upon what is given, you can calculate. Usually, related to electricity, these are the terms I, V, I and R, and then the time taken. So, using these information, you can calculate the electrical energy using this formula. Is it clear, children? So that is the first information that we are going to mark in your book. Okay. So electrical energy supplied by the source is equal to, okay, either you take it as electrical energy instead of W, you take it as electrical energy, E. Electrical energy. The next information is SI unit of electrical energy is Joule, symbol capital J. Okay, the next term that we are going to see is power. Okay, another term related to electricity is power. Okay, so we say very often there is power cut and all that. Okay, so power is another term which we use very often with electricity. So what is electrical power? You know the formula for power. Power is work done upon time or energy upon time. Right. So in these formulas, if I divide it by time, so power will be VIT by T, I squared RT by T. It will also be equal to V square by R into T upon T. So all these T will get cut. And so the formula for power will become V into I, or it can be I squared into R, or it can be V square upon R. These are the three formulas for electrical power. These are electrical energy, VIT, I squared RT, V squared by R into T. This is VI, I squared R, or V squared upon R. Only T terms will not be there. Remember any one thing, then the other thing it's easy to remember yourself. Okay, now come to the book. Yeah, we have put a tick mark here. Electrical energy, three formulas. You need not write QV, children. Just write these three formulas: VIT, I squared RT, and V squared by R into T. Then for power, the three formulas that you'll be having is VI, okay, V into I, V squared upon R, I squared into R. Now, unit of electrical power will be watt. Okay, joule per second or watt. You have studied it before itself. Then 1 watt ka definition, that will be in, you have studied this in second chapter itself. Bigger units of electrical power are kilowatt, megawatt and gigawatt. Kilowatt is 10 power 3, mega is 10 power 6, giga is 10 power 9 watt. Now come to the next main topic, commercial unit of electrical energy. Commercial unit. Commercial means for business purposes, for calculating electricity bill and all. They don't generally use, though it is energy. Here we saw SI unit of energy is joule. SI unit is joule. But they won't use this unit to calculate practically electrical energy. Okay, so for practical purposes, okay, there is something called commercial unit of electricity. What is that? Joule will be a very small unit. Okay, joule is one way. For commercial purpose, the unit that they will be using is watt hour or kilowatt hour. Watt hour, R won't come, sorry. WH or kWh. Okay, from where are they getting this? Now, power is equal to energy upon time. So, energy will be power into time. So, power is in watt, time is in hour. If I take power in watt and time in hours, that will give me watt hour. And if I take the power in kilowatt and the time in hours, that will give me the other unit, kilowatt hour. These are not SI units, but these are called commercial units. For all calculation of electricity bill, these are the units that are generally used. Okay, so now, so you have to underline this. Electrical energy is measured in bigger units, that is watt hour, WH and kilowatt hour. These are called, these are the commercial units of electrical energy. Okay, then 1 watt hour is how many joule? Okay, 1 watt into 1 hour, that is 1 hour if you convert it into seconds. Okay, because 1 joule is 1 watt second. 1 watt, okay, here power is energy upon time. So basically energy in joule and time in second. So this is what we call watt. 1 watt is 1 joule per second. Is it clear? So, but we say 1 watt hour is equal to 1 watt into 1 hour. So that will be 3600 joules. So 1 watt hour is 3600 joule and 1 kilowatt hour is, okay, 3.6 into 10 power 6. This into another 1000. Multiply it with another 1000, you get this. So these are these two conclusions you have to know. Okay. Now, come to the next topic, power rating of some common electrical appliances. Power rating of some common electrical appliances. If you see in any electrical appliance, suppose your refrigerator or your geyser, so in those things there will be a metal slip, like in a geyser you can see this. Okay, there will be a metal slip kind of a thing on which some things all are written. Okay, some informations, numbers will be written. So in this, two main information will be, it will be usually given 2000 watt 220 volt. 2000 watt 220 volt. This information is called power rating. This information is called the power rating of appliance. Power rating means every appliance, okay, when will be provided with a particular power and voltage. This is power and this is voltage. So every appliance, if it is a refrigerator, it will be written 150 watt 220 volts. On a refrigerator, this will be written. Okay. Press box, maybe 800 watt. Press box, it will be written 800 watt 220 volt. This is the power rating of refrigerator, power rating of press box. Okay. So what does it mean? What information does it give? This means if you give 220 volt, now you know that normally the supply that we get, okay, from our 3-pin plug, okay, the supply that we get from electricity, the electricity pole is 220 volts. So power rating gives you this information that, okay, in India we are supposed to get 220 volt in all our 3-pin plug, but many times it will be 210, 200, 180, okay, low power, or sometimes it even goes to high power. That can lead to some damage and all that, but on an average we are supposed to get 220 volts in every power plug. So when you insert an appliance inside, you're getting 220 volt as the input voltage. If that much voltage is given, then that appliance, if it is a refrigerator, it consumes 150 watt in 1 hour. In 1 hour, it will consume 150 watt. If it is a press box, and if I supply 220 volt, then it will consume 800 watt in 1 hour. That is the meaning of power rating. Okay. So the definition of power rating is not very clear. I want you to note it down. Define power rating. Define power rating. Every electrical appliance is rated with its power and voltage. Every electrical appliance is rated with its power and voltage. You can pause it and write it. I'm reading it fast. The power consumed by the appliance will be equal to the power rating only when it is connected exactly to the voltage rated on it. The power consumed by the appliance will be equal to the power rating only when that appliance is connected exactly at the voltage rated on it. In the sense, if only 220 volt comes, it will consume 150 watt. If suppose 210 volt or 200 volt is coming, in India all this is possible, low voltage, high voltage, all that is happens. So 200 voltage is coming, then it won't consume 150 watt, maybe only 130 watt or 140 watt it will consume. So that is what is the meaning of this. So if they ask you define power rating, you have to write this information. And another thing, kind of question that they ask in this is, what do you mean by an electric bulb is rated 100 watt 220 volt? What do you mean by this? Okay, this is the question. What do you mean by this? It means, what you will write, if the bulb is lighted on a 220 volt supply, the power consumed by it is 100 watt, not energy, it is power. The power consumed by it is 100 watt. So that is the information that it gives. Now, from power rating, you can calculate two things. One is the resistance of the appliance, and then you can calculate something called safe current. Safe current. Okay. Now, resistance. Now, P and V. Okay. So, the formula for P. Formula for P is I squared R. One of the formula for P is I squared into R. Okay. So, we know P and V, right? No, not this. P is equal to V square by R. Let's take this formula. Okay. So, from this, R will be V square by P. Is it clear? So, I can calculate. If I know P and V, I can calculate the resistance using this formula. R is equal to V square by P. I can calculate the current using this formula. If I have to use current, I have to use this one. P is equal to VI. So I is equal to P by V. So safe current I is equal to P by V. Safe current means that is the maximum current that can flow through a appliance. If the current crosses this limit, then your appliance will get damaged. Your bulb will get fused and this can sometimes blast off. Okay, the filament will get melted. All that can happen. Okay, it's very, very important. Safe current calculation is very important. How much maximum current can flow in this particular appliance. For that, I use these two information and calculate. Okay, children. So one is define power rating. The other one, what are the two things that you can calculate from power rating? Two things that can be calculated: resistance, safe current, and these are the formulas used. Okay. They have given some example how they calculated that resistance and all that. Okay. Now they have given power rating of some common appliances that we use in our day-to-day life. Car filament, car bulb is power is 20 watt, voltage is 12. Okay, so that runs with the car battery. So it's a DC battery, so it will be very less. Okay, DC AC we'll see later. Now bulb, if you see, it can be 15 to 200. Like this you can have an idea. Fan 60 to 100, that means you have a regulator. If you keep it in low speed, it might consume less power. If you keep it in high speed, it might consume more power. Refrigerator 150, like that. So if you see the whole table, electric oven, OTG oven, it consumes 3000 watt. That's the highest power consuming. Even ACs, air conditioners also consume so much power. Okay, geyser is another, even 1500. You have bigger geysers can consume also 3000 watts. So this gives you an idea. If you use an electric oven for a longer time, your electricity bill will also be very big. That's the meaning of this. If I consume a bulb, it may not affect so much my electricity bill, but oven or a geyser, if I use it for longer time, because their power rating is very high, the electricity bill will also be very, very high. That's why in summers and all, if you're using AC, okay, your electricity bills will be really high. That's because of this high power rating. Okay, coming to the last part, that is Joule's law of heating. Joule's law of heating. According to this, heating effect of current, whenever current passes through anything, there will be heating effect. Okay, according to it, the amount of heat produced in a wire on passing a current through it is given by heat energy is equal to I squared R into T. I squared into R into T. Heat energy produced in a wire when current is passed through it, where I is current passed through, R is the resistance, and T is the time for which the current is passed. Okay, so Joule scientist gave this law that the amount of heat that is generated in a wire can be calculated using this formula. So that is called Joule's law of heating. Thank you so much, children.